Okay. So in the states of matter, the first part related with the gaseous state was gas laws. They should be well known. Now I'll talk directly with the questions which are asked. The first is Boyle's law, which stated that at a constant temperature, pressure is inversely proportional to volume. That is, P will be equal to K by V, or PV, the product of pressure volume, will be equal to a constant. And if you are asked numericals with respect to two data, then apply P1 V1 is equal to P2 V2. Then there are graphs which are asked with respect to Boyle's law. First, pressure versus volume. If they are inversely proportional, its graph will be rectangular hyperbola or exponentially decreasing. Second, they can also give you a graph of pressure versus the reciprocal of volume, or 1 by V. Now, P with 1 by V are directly proportional. So, if two variables are directly proportional, it is y equal to mx type graph, meaning a straight line passing through the origin. Thirdly, if the graph is asked of PV, pressure volume product, versus pressure or volume, then its product will be constant irrespective of the change in pressure or the volume. P into V will be a constant. PV is a constant, and when there is a constant, it will be a straight line parallel to pressure or volume axis, and this is equal to K. So that's a part of Boyle's law. There is one more part. If PV is equal to constant, take derivative with respect to volume. So if I take the derivative, it's application of UV rule. So P into dV by V, that's 1, plus V into dP by dV equal to derivative of a constant equal to 0. Understood? UV rule apply kiya hai. P into derivative of volume with V, that is 1, and V into dP by dV. Therefore, dP by dV, meaning the change in pressure with the change in volume, is equal to minus P by V. Minus P by V.
We can say like that the Barnes modulus is equal to minus P.
Yes, it's similar, yes. And this basically should be represented at a constant temperature. So what we write as a statement for Boyle's law is dP by dV at constant temperature is minus P by V. Now P in terms of V is equal to K by V. So if I substitute here, it will be minus K upon V square. Meaning in the options you can get dP by dV at constant temperature equal to minus P by V or minus K by V square. They are both valid expressions of Boyle's law. That's important. Clear? Next, Charles' law is stated at a constant pressure, volume of a gas is directly proportional to temperature. It also stated that, Charles also stated that the volume occupied by the gas increases or decreases by 1 upon 273.15 times the initial volume or the original volume after every degree rise or fall in temperature. So the expression related with that is volume at a temperature T degrees Celsius is equal to the original volume at 0 degrees Celsius, that's V0, plus the increase is 1 upon 273.15 times of V0, but this was for every degree rise, increase in temperature or decrease in temperature. So here for a T degree Celsius temperature, it will be T upon 273.15 into V0. Clear? So now from this expression, if the volume is decreased to minus 273.15, at that low temperature, the gas molecules would be coming ekdam dur. They will come very, very close, and at certain point they can get liquefied, and at very low temperature they can even get solidified. Meaning the behavior of the gas at certain temperature or lower temperature will change. It will not be similar to the behavior of the gases. Clear? So now when you draw the graph for Charles' law, it's very interesting to note. There are two graphs. One is volume versus the temperature in Kelvin. Now if I take the temperature in Kelvin, the volume at minus 273.15 degrees Celsius is becoming how much? Let's substitute this over here.
It is 0.
It's 0.
From origin.
Correct. And this 0 is the volume at minus 273.5 degrees Celsius, which is actually equal to 0 Kelvin.
Yes, sir.
Meaning when the temperature is 0 Kelvin, the volume is 0. Meaning here the graph will start from origin and it will be y equal to mx time. But if you are asked the graph of volume versus the temperature in degree Celsius, the graph will cross the y-axis and meet 0 at a negative side. Because in this case, when the temperature is decreased to minus 273, then the volume is becoming 0. So the graph for volume versus temperature here will be like this. Now they also ask you why dotted lines are drawn in this graph. The dotted lines are because at the lower temperature, the gas molecules are getting liquefied or solidified. The behavior is no longer similar to gas molecules. So here the behavior can't be predicted. That is why there will be the relation of V proportional to T under a certain range of temperature. At the lower temperature, the behavior can't be predicted. For that, a dotted line is indicated.
So how do we get 0? We put T as 273.15.
T as minus 273.15. So at the temperature minus 273.15, the volume is decreased to 0. And that itself is the absolute Kelvin temperature or absolute 0 of temperature, 0 Kelvin. And this is also related with third law of thermodynamics, if you remember. Third law, the entropy of a perfectly
Solid is
solid is 0 at absolute 0 of temperature. That absolute 0 is nothing but 0 Kelvin or minus 273.15 degree Celsius. Now here also derivative की अगर बात करूँ, then V proportional to T gives you V equal to KT. If I derive it with respect to T, then dV by dt is equal to a constant K, and this is at a constant pressure, Charles law. I have derivated with respect to temperature at a constant pressure. So this is also a valid expression of Charles law. Clear? Third was Avogadro's law. Avogadro's law states that equal volumes of different gases occupy equal or same number of moles under similar conditions of temperature and pressure. So mathematically, at constant T and P, temperature, pressure, the volume is directly proportional to number of moles. And for 1 mole of gas, it always occupies a standard volume equal to 22.414 dm³. So that's how the Avogadro's law was related. Then there is Gay-Lussac's law, not of combining volumes but with reference to gases. Correct. Under the similar condition of volume, meaning at a constant volume, pressure is directly proportional to temperature. That is Gay-Lussac's law. Okay. Then when we combine all the gas laws, we get an ideal gas equation. And the ideal gas equation is famously PV is equal to nRT. Z is for the real gas. We'll come to that. PV equal to nRT is for ideal gases only, and that's valid for ideal gas, not the real. PV is equal to nRT. ठीक है. Now यहाँ पे R का जो value है, that will be equal to 8.314 in the SI unit of joule per mole per Kelvin, or 0.08206, which can be approximately taken as 0.082 liter atmosphere per mole per Kelvin, or it can be taken as 2 calories per mole per Kelvin. It should be clear because thermodynamics में we have talked about this R का values.
Boltzmann constant.
हाँ, that is K by NA.
K by R.
R by NA is K.
That is to
वो काइनेटिक थियोरी में बताऊंगा.
2 into 10 is to minus.
काइनेटिक थियोरी में करेंगे. अब आइडियल गैस इक्वेशन से कुछ इंपॉर्टेंट रिलेशंस. मान लो बॉयल्स लॉ में दिस ग्राफ इज गिवन एंड देयर आर 3 कर्व्स are given and they are at different temperatures T1, T2 and T3. You are asked to compare the relation between T1, T2, T3. मतलब is this a lower temperature or is T3 a lower temperature? अब इसका एक शॉर्टकट है. Listen carefully. सबसे पहले draw a vertical line parallel to the y-axis. Now जैसे ही मैंने vertical line parallel to y-axis किया, I have kept the volume to be constant. Now the moment I keep the volume to be constant, basically I am changing this to the Gay-Lussac's law condition. ठीक है. अब इसका शॉर्टकट तरीका क्या है? We know that PV is equal to nRT, ideal gas equation. What I have kept constant? Volume. So V निकल गया. R is a constant anyways. N, the number of moles of the gas is constant because it is always fixed mass of the ideal gas. So what we now get is P and T directly proportional. That's Gay-Lussac's law, correct? So now with respect to T1, if I correspond to the pressure, this becomes P1, this becomes P2 and this becomes P3. And from the range you can see P1 is larger, so T1 has to be larger. Hence the answer will be proportional, na? T1 greater than T2 greater than T3. A very very important question from Boyle's law. Same lines में Charles law में there are 3 linear lines which are given and they have mentioned the pressure condition P1, P2, P3. Again, how to start? Draw a vertical line parallel to y-axis, meaning you made the temperature to be constant. Now it's a special case of Boyle's. So P and V are inversely proportional. So now correspondingly this is V1, this is V2 and this is V3. If V1 is greater, P1 should be smaller. If V1 is greater, P1 should be smaller. P1 less than P2 less than P3. Same can be done for Gay-Lussac's law graph also. Because Gay-Lussac's law में constant volume पे P is proportional to T. So when you draw a line parallel to the y-axis, you are making temperature to be constant. And when temperature is constant, P and V are inverse. You get a case of Boyle's law. Clear with that? Ideal gas equation PV equal to nRT. Now N is the number of moles, which is equal to given mass by molar mass into RT. If I rearrange this as P equal to W by V into RT by M, then V per unit volume is
concentration.
Density.
Density.
So this is equal to dRT upon M. So you are asked to find density from the ideal gas equation. Then the expression what you get is Pm by RT. बहुत important formula है. No need to actually remember. I have just given you a simple derivation. Moles is weight upon molecular mass. So I have taken the volume down, weight by volume density. So density is equal to Pm by RT. So molar mass for a particular gas would be given at a pressure and temperature. You can just calculate using this relation. Now in this, the molar mass ka unit will be substituted as
Grams.
If you substitute in grams, then the density will be gram per liter. But the SI unit of density is
Gram per cc.
kilogram per meter cube, SI unit. Hence the molar mass over here has to be substituted in kg per mole. Generally we have the values as gram per mole. मतलब ऑक्सीजन के लिए molar mass of O2 is
32 grams.
32 gram per mole. But substitute करने के लिए it will be 32 into 10 power minus 3 kg per mole. So whenever you have the molar mass in the expression, remember always to substitute in the kg, otherwise 10 के units में आपको गड़बड़ मिलेगा. ठीक है ना? इसी से एक और केस. If I have 3 gases, let's say A, B and C, which are non-reactive gases enclosed in a container. three gases, non-reactive, enclosed in a container. The total pressure of the container would be equal to
Sum of the three
pressures, and these pressures are called partial pressures. These partial pressures are in turn related with total pressure as
mole fraction into total.
mole fraction. This is nothing but the Raoult's law which we have studied, but here for this the name given is Dalton's law of partial pressure. Dalton's law of partial pressures.
So we have to substitute 32 tends to -3.
Yes. This molar mass has to be in kilogram per mole. So now Dalton's law is simply PT, total pressure, equal to PA plus PB plus PC, where this individual partial pressure PA is equal to XA PT, mole fraction into total. PB will be equal to XB PT, PC will be equal to XC PT. Clear? So that's Dalton's law of partial pressure. After Dalton's law, we also have Graham's law,
Graham's law.
and this is for diffusion. So when the gases are diffusing with respect to each other, the speeds of diffusion will be dependent on their molar masses. Heavier the gas, slower will be the diffusion, meaning the rate of diffusion is inverse to its molar mass, and that's what the Graham's law is. The rate of diffusion is inversely proportional to square root of the molar mass. It's square root of the molar mass, or it can also be related with the density, that is R is inversely proportional to square root of the density. So if you are given two gases, then the ratio of rates of diffusion R1 by R2 could be calculated as root of M2 by M1 or root of D2 by D1.
So ये तो सीधा वो इक्वेशन से ही आता है ना, C is equals to root 3 RT by M.
हाँ, kinetic energy वाला KTG वाला expression. Okay, so R1 by R2 is root of M2 by M1 or root of D2 by D1. If the number of moles are different, then it will be N1 by N2 into root of M2 by M1. So if the number of moles are assumed to be same, then it will reduce to this. If the moles are different, we will calculate as N1 by N2 root of M2 by M1. Also, the rate of diffusion can be defined as the change in volume with the time, or you can take it as change in pressure with the time. So you might be given about two gases, its volume change for a particular time period, and the rates of diffusion ratio need to be calculated. So you can first calculate R1 by R2 using any of this expression, and then take delta V upon delta T ka ratio, and one of the things would be asked to calculate. So that's about Graham's law of diffusion.
That's equal to -9.
Equal. Meaning either you take the change in volume with time or change in pressure with time. Okay, next the kinetic theory of gases. Now there were many postulates of KTG, kinetic theory of gases, but the two important postulates were: when the molecules are present in a container, they don't have any force of interaction between them, neither attraction nor repulsion. Secondly, the volume which is occupied by the molecules of the gas is very small as compared to the total volume of the container, or total volume occupied by all the gas molecule. So volume which is occupied by the gas is very small in comparison to the total volume occupied by the gas molecules, in the container. So the first expression which was important over here is kinetic energy is equal to half of mv square, and this v is the root mean square velocity of the gas molecules, and the PV expression was 1 by 3 m into v square. Therefore, when you take the ratio kinetic energy upon PV, you get 3 by 2, and therefore the kinetic energy in terms of PV is 3 by 2 PV, or PV equal to nRT, 3 by 2 nRT. This is the total kinetic energy of all the gas molecules in the container. So KE total is 3 by 2 PV or 3 by 2 nRT. Now it is asked the total kinetic energy is dependent on
temperature
volume,
and moles. It's independent of pressure.
it's here it is proportional to P and V and here it is proportional to N and T. Matlab, with respect to this important expression, it's proportional to the absolute temperature in Kelvin. Never ever substitute the temperature in degrees Celsius. Even when you take the ratio, let's say Charles law mein two temperatures are given, 100 degrees Celsius and 200 degrees Celsius. The ratio of that will not be 1 by 2. 273 by 373 by 473. It will be obviously different. So remember, never ever take the temperature in degrees Celsius. In any of the formulas, we are not taking the temperature in degrees Celsius. It's always the absolute temperature in
That
Kelvin.
means larger the gas or more energy you have.
Larger the, higher the temperature.
So N now.
N is moles which is given mass upon molar mass. Molar mass से तो inverse हो जाएगा. Inverse हो जाएगा. So the kinetic energy total is 3 by 2 nRT. Now if you take the N down, then we get kinetic energy per mole. That is called KE bar. Bar means average kinetic energy. And the average kinetic energy is equal to 3 by 2 RT. 3 by 2 RT. Now this is very important. If you are asked about two gases and their average kinetic energies,
Dependent on temperature.
it's just dependent on the temperature. So if the temperature is also same, the ratio of their kinetic energies will be
Unit.
1:1. But if the total kinetic energy ratio is asked, it will be dependent on the number of moles at a constant temperature. So here if the temperature changes, the KE ka ratio will change. But average kinetic energy at the constant temperature for different gases is going to be same. Very, very important. Okay? Now, if this kinetic energy is asked for one molecule, listen, three variations important hai. Total kinetic energy, average kinetic energy and kinetic energy for one molecule. So if I consider N to be 1 mole, I am talking about Avogadro number of molecules. So total energy will be 3 by 2 NaRT. Barabar? But for one molecule, you should divide by Na. So what you get for one molecule is 3 by 2 RT upon Na. But this R by Na ratio is
K.
Boltzmann constant, which is K. Hence, the formula reduces to 3 by 2 Kt, where K is Boltzmann constant equals to R by Na.
That was 1 point something.
So how do you
8 upon, for one molecule, you should divide by Na.
Now to 1.3. 1 point.
हाँ, मतलब into 10 power जो है -23 आएगा and it will be 1 point something approx. But ज़रूरत नहीं है वो. K क्या है वो याद रहना चाहिए if you are asked. So it will be 3 by 2 Kt. So remember three expressions. Total is 3 by 2 nRT. Average is 3 by 2 RT. For one molecule it is 3 by 2 Kt. 3 by 2
1.38.
Kt. Almost 1.4 लेके कर सकते हो.
So N you wrote 1 by Na. So how?
हाँ.
So N you wrote
For one molecule ना. Single molecule मतलब I can just divide by the Avogadro's number.
N.
See, for one mole, I have 6 into 10 raised to 23 molecules. So one molecule के लिए how much?
1 by
1 upon Na. So one molecule is 1 by Na. Now we have different velocities of gas molecules through the kinetic theory. We have RMS velocity, root mean square velocity, average and most probable. RMS, average, most probable. Now they all have the formulas in term of RT by capital M. RT by capital M. So this part is constant. Now the difference here is in the factors. The root mean square velocity is 3 RT by m. Average is 8 RT upon pi m, meaning the ratio is 8 by pi here. And most probable is 2 RT by m. So now, yes, you can actually remember it as RAM. The ratio, in fact, if you take is root 3 is to root 8 upon pi is to root 2, which is 1.73 to 1.6, 1.4. Hence, if you are asked to compare, RMS is greater than average is greater than most probable. So can be remembered as RAM, and just you have to remember 8 by pi and 2. 3 velocities are important, and this is a ratio. Very important, here the molar mass should be in what unit? kg. Wherever you have capital M, molar mass, remember you have to substitute in kilogram per mole. सबसे silly mistake होता है in terms of substitution only.